All right. Okay, so welcome back. All right, so how's everything going? Good? All right, any plans for the fall break? Do you guys have any plans? Like, anybody's doing anything fun? Right? Project? Assignment? Okay. Midterm? Good news about the midterm. I'm not sure if it's good or not. There's a slight change in plans. There will be a midterm, don't get too excited. It will still be a midterm. But it's going to be on October 23rd instead of October 18th. I don't know why you're applauding that, but it's fine. So as you defer, okay, but this is final, okay? So October 23rd is Monday, okay? Please.
What's the submission link of the project release? Submission link of the project.
Yeah, it will be released. Yeah, no worries. So I believe the first phase of the project is going smoothly, right? The second phase will be posted immediately after phase one, okay? And it will be a lot of work, so I hope that you guys start working on it as soon as possible. And with the phase two of the project, we'll also give you some instructions of how to access the cluster. It's basically, we have two cloud service providers, and they will give us cluster support, and we'll give you instructions. It should be easy. It's nothing like very complicated. This will come with phase two of the project. Any other questions? Please.
Can you give some sample questions
So the question is, can you leave some sample questions for the midterm? And I will talk to you about the midterm. I will receive questions, but I have no sample questions for the midterm. Like sample midterm exam or anything like this, you will not receive that. Okay? But we will have a discussion before the midterm. If you have any questions about what kind of questions, anything, I will definitely answer it. Okay? Other questions?
So,
Please.
So the midterm will be mostly from the slides.
The midterm, yes. All what you'll be asked for is everything in the slides and everything I said and we discussed in class. Okay? Nothing outside of this. Sounds good? So, which means that if you've read any book or any research paper about any topics that you found interesting, this is great. I encourage it. It's not going to be in the exam or anything like this. So, I'm not going to tell if there is something in the book, for instance, any book related to this topic, because there's several books, and one of them might give you like the chapter's recommendation or for reference. I'm not going to ask you anything that is extra in the book and is not covered in class. So which will make it easy because you have everything. You have the slides, you have the video lectures, and I'll make sure before the midterm you have all the video lectures uploaded, and also all the slides. So the video lectures, they have the slides in them, but I mean I also have the soft copy of the slides alone and the slides content in Blackboard, so that you have all the resources you need for your exam. In the exam, you will have a cheat sheet. It will be just one page, like one paper, A4 paper. Okay. We don't make it open book. We make the cheat sheet, and the cheat sheet is small on purpose, so that you know how. Like, if you have a small cheat sheet, this means that you need to put the smallest amount of information, and putting the smallest amount of information will force you to kind of study well and hence summarize well, okay, in the cheat sheet. So this is the purpose of the cheat sheet. It's actually, the purpose is not to help you with the exam, during the exam, is to help you actually study before the exam. Otherwise, I don't think it's going to be that useful, okay? But you never know, right? So there will be different kind of questions, and when we come close to the midterm, I will have like a session, like part of the session is to talk about the details of the midterm and get your questions, and so that you feel a little bit of relief before the midterm day. Okay. So again, that was change, just a few days change of plans for the midterm. It's going to be August 23rd, Monday. October, sorry. I don't know why, I mean, every time I talk to people these days, and every time I set a date, I say August. I don't know why. No, I hate it, it's too hot. It's for some reason, like my clock just stopped there. Yeah. It's October 25th. I apologize. All right. So that's for the exam. For assignment 1, it's already released. For assignment 2, as we speak right now, it's released. You probably see an earlier version of it, but it's now officially released. And the deadline for it is going to be after fall break. Okay? So you have more than a week for it, but because you have fall break, this is why we give you more than a week to... is it more than a week? I don't know. Just like, yeah. So it's going to be after fall break. Okay, any questions? The second assignment will ask you to implement 2 kind of queries on the fragmented data that you had in assignment 1. So in assignment 1, you implemented different fragmentation techniques. What you're going to do is that we're going to ask you to implement a point query, which is looking for a specific value in these tables, and how can you collect the data from different fragments over the fragmented or partition database. And we're going to ask you also to implement a range query. And the range query will take 2 values, and you find all the tuples such that attribute values within this range. So it's kind of simulating the SQL query somehow, with the select from where, and in the where you have an attribute and an equality. This is a point query, and in the range you have an attribute and you found the value of this attribute within a range. So it's simulating, these queries are simulating this kind of SQL query. It is as simple as this. Okay, there are of course a lot of details of how to access the data from different fragments that you already have in the database. So this is again the creativity in the assignment is in this side. So you guys have to think, how can I get the data, right, from different partitions and stuff. Also, this you might think about. Last time we talked about two-phase commit and how to achieve reliability and all these issues. We have to continue talking about that, but I'm switching gear just this time. Switching gears. I'm talking about a topic about parallel database systems because it's related to query processing if you have partition databases. So this is why I want to talk about it, and then we'll go back to two-phase commit and all the, continue talking about reliability, okay? Also, the last portion of the class today, I will ask you to provide what we call, what I personally call like kind of a midterm teaching evaluation. And it's an informal evaluation for the teaching. So while you guys share with me what you think about the course so far, and what you think how it can be fixed, if there's something that needs to be fixed. This is not the official course evaluation, teaching evaluation that we do at the unit or at the engineering schools. This is just between you and I. And of course, but it's still going to be anonymous, so you're not going to put your name on it. So you feel free to evaluate it. And I usually take that and see what I can do if there's something that needs to be fixed, right? Or if there's something good, how can I stress on it even more, okay? So this will be the last section of the class today. But now we're going to just talk about parallel database systems, a few concepts that we may need to know. In parallel data, and also today, hopefully, we're going to have a little bit of time to talk about parallel data processing, not only in relational databases. We're going to talk also about Hadoop and Spark, hopefully today, because this is also relevant to the project. That's the agenda for the class today. All right, let's get started. So parallel database systems. Let me ask you a question. So far, I've been talking to you about distributed database systems, right? Is there any difference between a distributed database system and a parallel database system, or there's no difference? Any ideas, any thoughts? So what is the difference between distributed database system and parallel database system? Please.
Parallel process information data.
So what's your
Ericsson.
just said that in a parallel database system, you process information in parallel, but in distributed, you just distribute the data across multiple sites, right? He has a point. So I partly agree. Partially agree. In a distributed database system, again, the focus is how, first of all, to distribute the storage of the data across multiple sites. So this has nothing to do with parallelization whatsoever, right? Distributing the storage of the data. The other thing is also distributed execution of the data. Distributed execution does not need to be parallelized. It could be, but it doesn't need to be. Okay? So you can do things in a distributed system without parallelization whatsoever. But it still need to take into account the fact that the data is distributed across multiple sites. For parallel database systems or parallel systems in general, the focus is you have a workload and you have multiple computers, multiple processors, and a processor can mean so many things. So I'm talking about like the processor general meaning of a processor. You have multiple processors, and you want the system for the workload that you have to parallelize the execution of this workload across multiple processors. And the main purpose of parallelization is to, again, speed up the process. In other words, database systems, the major workload is queries, right? You receive a lot of SQL queries coming into the system. In a parallel database system, one of the focuses is how to parallelize the execution of SQL queries, or any queries written in any query language close to the database. So select from whatever, any table, how can you parallelize this so that you get the answer faster if you have multiple processors in the system. So this is the main difference here. And again, there is overlap because if you have a distributed system, you have an opportunity to parallelize workload because you have multiple components of the system that each one can do something at the same time. But you can have parallelization without a distributed system. Like if you have multi-core CPU or something like that. So you can parallelize or a GPU. It's not a distributed system, it's a parallelized system, okay? You understand the difference? And you can still parallelize the execution of SQL queries or any database workload among different CPUs, like CPU cores, okay? Or the cores of the GPU unit or something. So that's the main difference between when we say parallel database systems and distributed database systems. So we agree there's an overlap now, and we agree that most distributed database systems, they have some sort of parallelization in them because they want to leverage the multitude of components and processors we have or computing resources we have in these distributed systems. So the question is, how can we do parallelization? How many of you have taken like a course on parallel processing before? Anyone? This one? Okay. So maybe some of the topics we're going to talk about today may be a little bit new to some of you, but it's straightforward. So the idea here is what kind of parallelism mechanism or approach we have to take into account. There are two main parallelism approaches that we might think of, especially in the context of database systems. There is the pipeline approach and there is the partition approach. Let's talk about the partition approach first. Partition approach means that you have, again, multiple computers and you have one task. Okay? So you partition this task among the computers that you have, or the processors that you have. So the task can be anything that processes data. You partition this task into multiple partitions, and each processor will do some processing on its own partition. That's partition parallelism, and that makes sense. And generally, when people think about parallelism, this is what the first approach you think of. But pipeline approach is a little different in the sense that you still have parallelized execution, but the parallelized execution is done in a pipeline fashion. Think of a factory or anything like this, and you have manufacturing pipeline. There are so many steps of the manufacturing process can happen in parallel, okay? But each step is do different things. So you pass a product into the pipeline, and this is the data. So one process in the pipeline takes care of does a task, while another processing do another totally different task. But the data can be fed in, and it depends on the number of processes we have. You can see many pieces of the data processed in parallel at the same time in the same pipeline. So this is called pipeline parallelism. So it's different. The partition parallelism is totally different paradigm. There is no pipelining whatsoever in this. So like you assume partition, and all these processors are doing the same exact thing at the same time to get the speed up you need. The pipeline, no. It's like this processor is doing one task, the other processor is doing a totally different, or like a relevant task also, and you have data item 1 is in processor 1, data item 2 is in processor 2, and they're both being processed in parallel. Okay. So this is one kind of parallelism as well. All right. What is the main purpose, again, of having a parallel database system? Speed up. That's the main purpose. So a little bit of theoretical figure here. So what is the definition of speed up? Definition of speed up means, it's already written here, so more resources mean proportionally less time for a given amount of data. What does it mean? So you have the same database, the same size of data that you have. If you add more resources, X resources, you get X speed up. That's what we mean by speed up. Resources here might mean processors. For the same size of the data, the same data, you don't change the data at all. The speed up, the ideal speed up is a linear speed up, which means I add one resource, X resources, I get X speed up. This is theoretical for sure. It's not always the case. But this is ideally, this is what we want to achieve. Sounds good? So that's what we mean by speed up. So what do we mean by scale up? So scale up again, you have, if resources increased in proportion to increase in data size, time is constant. So I increase the data, so the database size is not constant, I increase it, but corresponding to the size, the new size of the data, I added more resources. The system scales well if the time is constant. Okay. Make sense? This is what we mean by the system scales up. When we talk about parallel processing, these two terms are really important to us. Any questions so far? Am I making sense? Good. So given that, how many of you studied computer organization and architecture somehow? Good, so we understand how the memory works and how computers work. That's good. Otherwise, it would be really sad, right? Yeah. But that's good. We're good. So these are different parallel architectures. Again, from a general perspective. So we have three different architectures we might pick up. We have shared memory, shared disk, shared nothing. Shared memory architecture is a parallel computer architecture where all the CPUs, we have multiple CPUs, and all of them share the same memory space. You guys understand what I mean by share the same memory space, right? Shared disk, you have multiple CPUs. They don't share the same memory space. Each has its own memory space, but they share the same disk or the same secondary storage system. Shared nothing means the CPUs, they don't share, they have each processing unit has its own CPU, memory, space, and storage, secondary storage. The only thing they share is the network. So that means, what does it mean for each one of them? If you have multiple processors that share the same memory space, this means if one processor wants to communicate with the other processor, how does it do that? It's through memory, right? So we both have the same memory space, so I can have access to the same memory location that you just accessed or written something to it. You might have written a message to me in this memory location, and I have access to it. It's easy, I can go and check it. Shared disk, they have to share information that they share only through disk or through the network, sure, yeah. And shared nothing, the only way they can communicate multiple processing units is through network, which means I need to send a message through the networking system. right? So these are the three basic parallel computer architectures. And of course, if we're talking about parallel database systems, we're affected by all these architectures because the data is actually stored on disk, but to process it in parallel, you have to load it in memory and then parallelize the execution among the processors you have. So if you have a shared nothing architecture, to each unit that way will do some kind of processing and will parallelize this across. But if you need to share the state of the execution or something like this, you have to transfer messages across the network, right? So like think about these implications when you're running a database query or something. So what I want you to do right now is a very simple exercise. I want you to tell me, and again, while talking to your neighbors, what are the benefits of shared memory as compared to shared nothing? And what are the benefits of shared nothing as compared to shared memory? And when I'm talking about benefits, I'm talking about which one of them can scale easier, okay? Which one of them, from an implementation perspective, is more expensive or less expensive? And which one of them, if I'm building a database system today, and I'm doing it for any of these architectures, if I'm developing the system, which one is easy to program than the other one? So these are the things I want you to think about. So I want you to talk to your neighbor, and then in a few minutes, we will bring the discussion back to the class. All right. So what do you guys think? Raise your hand, please, if you're interested in sharing your opinion. Please, in the back.
Shared memory is faster compared to shared nothing.
Okay. Shared memory is faster.
In terms of accessing memory. It's any data.
Shared memory is faster as compared to shared nothing. Okay. So you say here, like, this is faster. Okay, other ideas. Please.
Shared memory will be expensive to implement compared to shared nothing.
Shared memory will be expensive to implement, more expensive, okay. And why is that?
Because you need a architecture, a particular architecture to implement that, and that architecture has some requirements that you have to specify, that you have to what you can say, like you have to implement a particular architecture for this memory. But in case of shared nothing, you don't need to implement any architecture. You can use an existing architectures and set the network among all the.
All right. It's close, yeah. But I'll come back to it. But what other ideas? Please.
Shared nothing is easier to program.
Shared nothing is easier. To program. And why is that?
We'll just add another client and we don't have to keep in mind of sharing the memory and implementing that.
Also close. Okay. Other benefits.
Fault impact in shared nothing is less as compared to shared nothing.
Shared nothing is what?
Fault impact. If any process goes down or anything, or there is any problem in the RAM, then in the impact in shared nothing, it will be just for a particular client.
You can achieve more fault tolerance here. Fault tolerance. Way in the back.
Shared learning is better when output of one process is not dependent on something else. If they are doing stuff independently. So
Shared nothing is better when the processing.
when the units are not dependent on other things for the
So when the workload does not lead to dependence across. Okay. So better. What do you mean by better? It's like faster. You mean faster when independent. All right. She started. Okay. Please. Yeah. No, you. Yeah.
Shared nothing is better for a scale-up because
So shared nothing is better. It's easy to scale as compared to shared, easier to scale. And why is that?
because new system with memory you need to add processors to it, but with shared nothing you can just add independent.
Very close. Yes. All right. Any other, please?
So in shared nothing, communication is difficult between the clients, whereas in shared memory it's easy because you can just use the shared memory.
So communication. What do you mean by easier and not easier?
So here there is a memory. The memory is shared. So if you allocate some memory,
So easier to program. You mean?
you can the different processors can communicate.
Okay, folks. Let's just do something now. So let's go on them one by one. Shared memory is faster. Is this true or false? Who thinks it's true? Who thinks it's false? Who thinks it depends? The same people that says true said it depends. Okay. Let me give you the answer. Shared memory or shared nothing. There is no one that is faster than the other. Okay? It depends on the workload that you have. And it depends about like what kind of resources each one have. Like if both of them, the collection of all the shared nothing computers have the same computational power as the shared memory. Okay? And there is no communication whatsoever in the workload sent across the network. Will it be the same? Right? It actually can be even faster because there is no, like, in shared memory you need to lock memory. And if you lock the memory, sometimes it's not available for the other processors. It can be even faster. Okay? So, both of them, it depends. There is no one that is faster than the other. It depends. Okay? So, this one depends. Okay, let's take a look at the second one. More expensive. More expensive in dollar cost. If you want the same exact computing resources, what I mean is like the same CPU resources, the same memory size, the same disk size, and everything. If you have a shared memory architecture and a shared nothing, which one do you think is going to be more expensive? Do you think shared memory is more expensive or shared nothing? So, who thinks shared memory is more expensive? Who thinks shared nothing is more expensive? Okay. For this one, I'm saying that shared memory is more expensive. Okay? Why is this? Since you guys study computer architecture, like computer organization, back at the time, we didn't have multi-cores. Okay? Now we have them. Everything's great. But having the same exact computing resources as shared nothing. Shared nothing means basically is that you have one computer and you add another computer to the network, another computer, which you can actually do that forever. It's as long as the network can contain all of this. Okay. Putting more processors in the chip is actually very expensive. Not only this, putting more memory in the same board shared across all the cores, or all the CPUs you have, is also very expensive. Not only that it's very expensive, the hardware technology cannot accommodate even more. You cannot increase the size of your memory in the same computer or the same computing units. There is a limit to the hardware, to the physics, right? So Intel and AMD and all these, they still cannot create for you 100 terabyte RAM. Okay? It's hot in the same board. It's hard to also have this amount of shared memory between all these CPUs. Also, not only this, also the buses that connect the CPUs to the RAM, it's actually very expensive to get in. The hardware architecture and the physics behind it is still really hard to scale to that huge scale. So it is more expensive to have a shared memory architecture with the same exact shared nothing, especially if you have a very large scale shared nothing cluster. Like if you have 1,000 machines and each machine has a 1 terabyte RAM. You cannot do that here, actually. So shared memory is more expensive in terms of dollar cost. So this is good. Easy. Please.
Somebody can make the argument that it depends again, right? I mean, up to a certain threshold.
Yeah, up to a certain threshold, it depends on what.
I mean, you said of a shared nothing network of a certain size, right? Well, up to a certain size, wouldn't the argument be made that it'd be cheaper to have a single machine versus, I mean, once you pass that
If you have a
threshold,
single-
of course, it's cheaper to, for example, a machine with 4 cores and 100 gigs of RAM, you can buy that probably cheaper than what it would cost to get.
I wouldn't say so.
You don't think so?
I don't think so. Anybody here works at Intel? Oh, sorry. Yeah, you work at Intel. Okay. So, I was just going to ask somebody working at Intel whether they think or AMD or anything like this. Based on my experience with machines and stuff, and based on the theory even behind it, it's more expensive to put more cores on the chip than buying small computers. So if you buy small computers, theoretically, it's less expensive than putting more CPU cores on the chip and have this shared memory and have these shared buses, right? And the problem gets even more complicated. I agree with you. The problem is amplified even when you have, again, when you go very large scale, because it gets even impossible after a while for the shared memory. So this is I'll agree with you on this. But theoretically speaking, putting more computers on a chip is more expensive than buying small computers and put them together. Okay, dollar cost, please.
Also, that if you want to include a new architecture of processor and memory, then the testing of that particular architecture will also require some time. That will also.
If you want to add, that's the next. Okay, you jump to another issue here, which is relevant. Shared nothing is easier to scale for sure, and it's related to the same arguments we're talking about here. So if you have a computer, yes, let's assume I have money, and I can get one computer that has like a gazillion cores in it, and I can have a very large memory. So, great. I think because again, if you have just one machine, some people think if you have one machine, it's way easier to manage something, which can be sometimes true. So I would do it. But what if my company, like you have your startup and you started with a server that has these fancy multi-cores and a lot of memory, and then your startup all of a sudden became Google. What's you going to do then? You need to scale. You need to scale your system. To scale shared memory architecture, what you're going to do? If you want to still stick to shared memory architecture, what you're going to do is you're going to take that chip, just throw it away, buy a new one that is bigger, right? If there is, and then you scale. While if you have a shared nothing architecture, what's going to happen? The network, the same network pretty much, okay? You're just going to hook up a new machine into the network. It's a shared nothing architecture, it doesn't matter. And it's a small, now I have 1,000 new customers, I'm going to add 2 more machines to accommodate these, right? It's easier to scale. The other one, yes, it can scale, but it's way more difficult to scale than the other one, and more costly even. That's a good point. All right, so this one is okay. So what about easier to program? So do you think shared memory is easier to program? If I'm developing the database system itself, okay, if I'm Oracle and I want to build a shared memory database system, like parallelized database system, which one is easier to program? Shared memory or shared nothing? Shared memory? Okay, who thinks it's shared memory? Okay. Some people are hesitant. Who thinks it's shared nothing? Okay, I see some abstain votes here. Okay. It's generally, if you talk about generally speaking, based on my experience also, right, working in both architectures or in real life, it's easier to program a shared memory architecture. Okay. Why is that? When you have a shared memory space, debugging even is way easier. You guys have developed, like you've taken programming classes. Almost all your programming classes, you're building programs in the same memory space. Pretty much, I would say so. I'm confident to say that most programming projects that you've done, not all, most, are in the same, you build a Java program and it runs in the same shared memory space. Maybe you've done some multi-threading or anything like that, but it's still the same, which is difficult also to do multi-threading. Doing programming in a distributed environment, like this shared nothing environment, debugging is a very complex task. So if I'm developing the system to be a robust system, it requires more effort to do that. But once you build it, it's easier to scale up. It's going to be less expensive even to scale up. Does it make sense? Right. So it's easier to program. Did I say, somebody said easier here, but I said program, maybe I was wrong, right? So this is wrong. All right, so more fault tolerant. Is it true or false? Shared nothing is more fault tolerant than shared memory. Yes or no?
Yes.
Why? Last time we talked about fault, and we talked about fault led to error, and error led to failure, right? You guys remember that. So you guys think that shared nothing is more fault tolerant because?
Your mean time to failure across multiple machines is compounded. It goes way down as you add machines.
Sounds good. So let's talk about this a little bit. It's a great point. I like the discussion that we're having. If you have one component in the system, and you have another system that has 10 components, the probability of failure is higher in the one with the 10 components or the one with the 1 component? Probability of failure. Mathematically speaking, the probability of failure is higher in the 10, which means as long as the more components you have in the system, the probability of failure is higher because you have more components that can fail. I'm not saying they're going to fail, but the probability is higher. So in a shared nothing architecture, the probability of failure is higher. But as the gentleman mentioned here in the back, even though the probability of failure is higher, but if taken care of well, you can leverage the availability of multiple components to recover from failure. So if you don't have, in other words, if you don't have a fault tolerance strategy in both of them, like the one with the 1 component and the other system with the 10 components, the possibility of failure is way higher in the 10 components, 10 times higher. Okay. If you don't have fault tolerance strategy. If you have the good fault tolerance strategy in the shared nothing, okay, you can actually take into account faults very well and handle them very well. Leveraging even the multiple components that you have. So again, fault tolerance strategies here are different than there. It's more difficult here. There are challenges here to fault tolerance, but there's also opportunities. It's a little bit tricky when you think about these kind of things, because if you have a distributed system, if you have a huge cluster like in Google or Facebook or anything, and all the processing is happening on hundreds, if not thousands of machines. That means that they encounter a failure all the time. but they have a really good recovery. They have really good fault tolerance in the system. They account for that very well. Sounds good? Thanks. So we talked about that. So faster, we talked to depends. So again, independent, this is one thing in the independent list. Because if you don't have a lot of communication between multiple components in the shared nothing, you can get things way faster that way. But if you have a lot of communication, this means a lot of messages sent across the network, and that means a lot of cost added to the execution, a lot of time added to the execution. All right. Make sense now? Good. All right. Back to database systems. So now that we discussed different computer architectures and how to do parallelization on different one of them, and how talked about really important issues about scaling up and cost and speed and all these kind of things. Now, what are the different types of parallelism we can do inside the database engine? So, as we talked, every query is, when you execute it, we talked about this in the optimization of queries, right? There's a query tree that you built, and the optimizer finds the best query tree. The query tree has operators in it. These operators can be selection, join, projection. So, in the database system, you have intra-operator parallelism. And that means that you take one operator in the tree, and you parallelize the execution of this operator. You go up to that level for sure. You have inter-operator parallelism. You have multiple CPUs, multiple components, and you can ask each of these CPUs, for instance, to take one operator and run it. Okay. So this is one kind of parallelism also. So each CPU is doing one operator. Or inter-query parallelism, so that you have multiple queries running. Each CPU will take one query and process it. It's not as naive as I say it now. It's more complex, but these are the different types, and all these types can be existing in the same system. Make sense? All right. We have seen this before, but it's also very relevant when we talk about parallelism. So, how a very good partitioning method will contribute to the performance of a parallel query processor. What do I mean? Like now, we have a table and we're running a query on this table. But I want to decide, and I'm following the partition parallelism method. And I want to decide how each CPU, what kind of data each CPU will work on in parallel. This is the decision. Which means that I need to partition the data to do the parallelization. How can I do the partitioning? We studied these several partitioning, and you guys implemented some of them in the fragmentation. So one of them is called the range partitioning. And range, basically what it does is that take one attribute or multiple attributes, and it partitions the data based on the value of this attribute. Each partition represents a range of values. You implemented this in assignment 1. Round robin is easier than that. All what it does that let's assume I have 10 processors. What I'm going to do is that I'm going to assign tuples from a table to that processor in a round robin fashion. So processor 1 take tuple 1, processor 2 take tuple 2, so on and so forth. And you parallelize the execution of the operation based on these partitions. Hash partitioning is more similar to range, but instead of just partitioning by the range values, you have a hash function on any of the attributes in the table, okay, or all the attributes. And this hash function decides which processor should take which piece of the data. It's basically simple hashing that you studied before in data structures or algorithms class. And again, the hash function can be more complex, can be simple, doesn't matter. This is not what we're talking about. So these are the different ways to do partitioning. Again, a good partitioning method, what do we need in a good partitioning method when we want to parallelize the execution? Please.
Partitions should be like equally weighted, like you should have equal data items. One should not be, it should not be sparse.
The partitions should have equal data items. So the gentleman here mentioned that he wants to make sure that each processor is being treated fairly. Each processor works on the same amount of data. We call this load balancing, right? Exactly. So this is a technical term. So I want, in a parallel database system, or in a parallel system in general, I want to make sure that the load is balanced. And the load is balanced depends on, first, I want to make sure that the data is evenly partitioned. But that does not usually guarantee load balancing, because it depends on what kind of operation each processor is running on the data also. Because I might have the same amount of data, but one processor is doing a very complex computation on this data, so the load may not be balanced either. So the load, to balance the load, it depends on the size of data that each processor is having or working on, and also on the task that this processor is doing on this data. So good partitioning methods will achieve the first thing, which is make sure that everything is evenly partitioned across, and to achieve load balancing. Okay, what else? I mean, what is a good thing about parallel, like a good quality or that we need for a partitioning technique? Again, you need to make sure that if there are more computation happening, you need to make sure that each processor spends the same amount of time on the data that is retrieved. That's the second part. And this depends on the workload coming to the system. So the workload needs to ensure that the system, to have a good partitioning, it needs to take into account the data, but also the workload. Workload in terms of queries or updates, whatever it is that you're doing, the operation that you're parallelizing. If you take these two into account, you're data aware and workload aware, the partitioning method will be efficient. Sometimes you don't know the workload. So this is a problem, right, for parallel database systems. So you collect statistics about the workload so that you, next time when you partition for parallelism, you do it better. You have the data. To be data aware is easier because the data, especially if the data is static, you totally know the ranges, and you know that, okay, the ranges are skewed around this value, so I'm gonna have a small range here while I get a bigger range for the other range of values because they're more sparse. This way I can make sure I'm fair across all the processors. Or I can assign, if the partition is small, I can assign two partitions to the same processor. It depends on how many partitions I have, how many processors I have. Usually people try to partition based upon the number of processors that you have, but it's not necessarily the case, right? Eventually, after all, these are logical partitions. You partition them based on logical value. Of course, they're being physically accessed by processors later, but again, the partitioning method is logical, based on logical value. Okay, so the question for you, so in a database workload, which of these are like partitioning methods can be good? So if I have, for example, a range query, a query that selects data based on the range of values. Which partitioning will be better? Why is that? Why it's going to be better? Because of what? So the data is already partitioned based upon range. Okay? So if we have range partitioning, it makes sense. Even if this range is high or big, you can still achieve parallelism if you're going to access the whole data. But if the range query accesses a few selection of the data, you know that you're assigning the task to the processors, or a couple of processors that really have the data, and it's easy. It's way easier to do the range query on these partitions. Again, because it's naturally range partitioned. What about if we have an equality join? A join that says, I want to select from table A, or table R, and table S, such that the join key is equal to the join keys in the other table. So which one is better? It's actually, arguably, I will say it depends again on the values of selectivity, but generally speaking, I'll say equi-joins are better if you have a hash, because you hash on a single value, and if the value you're hashing on is that joining key, to be even better. But range also partitioning can still be good. What about round robin? What is it good for? What's that? Round robin, I will say, it is an amazing partitioning strategy if the workload that you have access the whole data all the time. Why? You achieve parallelism. Not only this, you achieve load balancing, and it's very easy. So if you have, for example, if your workload is scanning the data, scanning the table, I'll do a round robin. Why do I need to do any other kind of partition? Like, because range and hash are smarter than the round robin, right? They do smart tricks. Round robin is very straightforward. So if your workload is scanning, round robin might be better. So also the architectures that you have makes a difference when you do the partitioning. What do I mean by this? Shared memory and shared disk are less sensitive to the partitioning method you use as compared to the shared nothing. The shared nothing architecture, they're both going to benefit from a good partitioning, but shared nothing, if you have a really good partitioning method, you can avoid a lot of communication across the network. So it's more sensitive to the partitioning than the shared disk and shared memory because of this kind of communication across the network. Sounds good? So a shared nothing architecture benefits more from a good partitioning. They all benefit, but this one specifically benefits more from it. All right, folks. I'll stop here, but now I'll ask you, please, like a paper and very simple protocol we're going to follow. You have two faces to that paper. The first, you're going to say what you like of the course so far, and the back, which is, I guess, would be more on it. So what you don't like about the course. Okay. So front and back. Very simple. You can use very simple language. You can use graphics if you want. It's okay. But polite graphics, please. Yeah. Yeah. Again, this is not going to the dean or to anybody. This is just going to me. And do not put your name on the top. This is anonymous.